So we can use calculus to find the max-min of relationships. So this is a good way to be able to then find the max-min or the optimization of problems. So here we have a relationship where we have an ellipse and we want to inscribe the largest possible rectangle inside of this ellipse. Okay, so let's sketch out this problem. Okay, so my ellipse has a major axis along the x-axis, so it's going to have a major axis of 6 and a minor axis of 2. It's going to look something like that. And then inside this, we're going to inscribe the largest possible rectangle in there. Okay, so there's our problem. Okay, so how do we find the area of this rectangle? Well, first of all, for any optimization problem, whether you're doing it with calculus or not, we need to come up with the equation that calculates the quantity we're maximizing. So in this case here, we're trying to maximize area. So we're going to do area is equal to length times width. Okay, well that's great, but I need this in terms of my coordinates, x and y. So I'm going to do this here like this. I'm going to maybe do a dot there, and I'm going to say that that coordinate is xy. So this coordinate being xy, then I can just say, well, the width is x, the height is y, so the area of this piece is just going to be x times y. And assuming I can maximize that area, I'm going to maximize the area of the whole rectangle. So I'm just going to simplify things, although I could just say 4 times a. I'm just going to maximize x times y. Okay, so x times y. But here, this is complicated because I still have too many variables to be able to optimize, be able to differentiate. So I'm going to then have to get rid of one of the variables. And that's where the other relationship comes in handy, because that other relationship allows me to get rid of one of the variables, express one variable in terms of the other. So I'm going to do that for y here. So I'm going to solve for y. So I'm going to get y squared is equal to 1 minus x squared over 36. I'm going to multiply that by 4. Okay, and then solve by square rooting. Now I'm going to get plus minus, but since I'm only going to use the top half of this ellipse, I'm just going to use the positive version of this. Okay, so there's my y value, and I'm going to use that now and replace that in this expression, and then I have my derivative or my equation as a function of x. So I can write this area as a function of x is going to be the width times my new expression for length, which is 2 square root, or my height actually, 2 square root 1 minus x squared over 36. Okay, so there it is. I now have an expression with variable x that for the area, which I can now differentiate and find the maximum area and find the x that gives me that maximum area. So the derivative of that means I just have to differentiate this. So I'm going to put the 2 on the outside here. I'm going to differentiate this. This becomes 1 times square root. Okay, so the derivative of x plus, apply the product rule, x times 1 over 2 square root 1 minus x squared over 36. I have to apply the chain rule, so it's going to be negative 2x over 36. Okay, so there's my derivative. So I want to solve this derivative equal to 0. Now it looks kind of messy, so I think I can see some ways I can simplify this fairly easily. I first of all can get rid of those. Okay, and I have this denominator square root 1 minus x squared over 36 times 36. So I'm just going to multiply everything through by that denominator, because since this is an equation equal to 0, Okay, I'm just going to make this, I'm just going to put the equal to 0 on this side. Okay, so I'm just going to multiply everything through. Because it's an equation, I can multiply both sides of this equation by that denominator, and I can clear out that denominator. And that, notice what's going to happen is that square root also going to get in the denominator is going to get rid of the square root in the numerator. Okay, so I'm going to multiply through by 36 square root 1 minus x squared over 36. Okay, so multiplying through then, what I'm going to be left with then, I got to be careful here, so it's going to be 0 equals, okay, so 36 times 2 is 72. Square root times square root is going to get rid of the square root. So I'm going to end up with 72 bracket 1 minus x squared over 36. Okay, so here I'm going to have x times negative x, so that's a minus. Okay, and then I'm going to have 36 cancel, the square roots cancel, so everything cancels out here. I have to remember to multiply by that 2 into the bracket, so I'm going to minusing 2x squared. Okay, so just double checking my work, 2 times negative x squared, yeah, and then 36 times 2, square root, that's going to get rid of the square roots. 36 times divide by 36, square root divided by the square root, they're going to all cancel. Looks like I have all my terms accounted for. So then going ahead and trying to solve this, I get 72 minus 72 divided by 36 is 2. So I end up with an equation that looks like that. And solving this for x, I get 72 equals 4x squared. Okay, so I get x squared equals, divide by 4, I get 18. And I get x equals plus minus square root of 18. Okay, which is basically 3 root 2. Okay, so I'm only going to use a positive version of that. I need to make sure I solve for y. Plug y into here. So 18, if I put square root 18 in here, I get 1 minus 18 over 36 is 1/2. Okay, so I get y equals 2, and I get square root 1/2. So I'm going to put this root 2 on the bottom here. Okay, so that looks pretty good. Then now I'm just going to go back to my diagram here, put in my dimensions, make sure I have my dimensions to make sure to find my max area. So the width, since the x value is 3 root 2, the maximum width along here is going to be 6 square root 2. And then the maximum height here is going to be double that, so it's going to be 4 divided by root 2. 4 over root 2. So my max area is going to work out to be 6 root 2 times 4 divided by square root 2. So the maximum area works out to be 24 units squared. Okay, so there's my maximum area worked out.